Here we go. Projections and vector components. This is super important. You're going to see projections all the way up until the last week of class. You really want to understand what it is. And it's one of the premier applications of dot product. And our physics brethren use projections all the time. That's how they do business. So what is it and how does it roll and how do you do one? First, I want to give diagrams on what it looks like when you take a projection of a vector onto another vector. So I'll start with, and I'm going to give you two different diagrams. That's why there's lots of space in here. So you're going to have u and v be non-zero vectors. And this stuff here, ignore that for the moment, the moreover sentence. Forget that for the moment. Let's just deal with the basics. So let's say you had a vector, oops, that's supposed to be kind of flat. There's a vector v. And let's say here's a vector u. What we're going to do is we're going to project u onto v. So we're going to project u onto the vector v. The result is going to be a vector. Now here's how I like to, I'm going to draw you a picture of this projected vector, but first I want to give you sort of the baby look of it, so you'll always know what this is. Pretend there's a bright sun shining directly overhead, and v here is flat on the ground, so this dotted line is the ground. What shadow would the vector u make onto v, where v is on the ground? So the shadow that v is going to make is this vector right here in blue. And folks, that vector, oops, that didn't work out, so it disappeared. That vector, this blue vector I have here, is the projection of u onto v. That is the projected vector of u onto v, that blue vector, okay? Now, this is what the picture looks like if the angle here, theta, is an acute angle, acute meaning between 0 and 90 degrees. What would the diagram or projection look like if the angle between u and v were obtuse? Okay, so new picture. We'll still have v on the ground here. So here's v on the ground. And u in relation to v is, let's say, pointing over here. So this angle theta is obtuse, aka greater than 90 but less than 180. We still have the ground here, and pretend again that there's a very bright sun shining directly overhead. What would the shadow of u look like on the ground? Okay, over now it's going to be this way. It's going to be pointing in the opposite direction of v, but this blue vector we still say is the projection of u onto v. Well, it's not touching v, it's pointing in the opposite direction. I don't care. That is the projection of u onto v, that blue vector. Now, I am going to refer to w1 as the resultant vector here. So this blue vector here is the w1 vector. The book doesn't use my notation, but we're going to give it a different notation here in a minute, but just let's call it w1. So that is the projection of u onto v. Now, w1 is called the projection of u onto v. And sometimes it's referred to as another phrase, and I need you to be comfortable with any of these phrases and vocabularies. A lot of times they'll call that projected vector the vector component of u along v. So either way they refer it, they just mean the projected vector of u onto v. Okay, now I'm going to give you the weird notation for it. W1 is sort of like a side notation. Proj, P-R-O-J, and then U, and then in tiny letters, because it's a subscript, V. And V is dropped down, it's tinier font, a little bit below the line, that the flat line that this is being written on. That is the subscript notation. So this means the projection of u onto v. Now be careful because order matters. This is different from a vector that would be, let's say I asked you to project V onto U instead, then the notation would look like this, proj V onto U. And those are two completely different vectors. Don't go, oh, it doesn't matter what order. Proj U onto V is the same as proj V onto U. It ain't. And a common student mistake is to accidentally, when I ask for, say, the projection of U onto V, they accidentally mess up the formula and they give me the projection of V onto U, and I give them 0 points partial credit. Those are not even close to each other, so you don't even get any partial credit. Sorry. I do like giving partial credit, but not in that case. Okay. Now, what's this W2 business? And why are we saying it's U minus W1? Let me draw a picture first so you get what he is. And by the way, our physics brethren care about all this entire stuff I'm talking about here all the time. I'm going to use a different color. How about pink? W2 is a vector that's orthogonal to V. Remember, orthogonal means like perpendicular. So it's making a 90-degree angle with V, and it's a special vector such that if you added W1 to W2, you would get back the U vector. Remember that this, if you use the parallelogram law, and if these two, W1 and W2, are adjacent sides of a parallelogram, in this case, a perfect rectangle, that's a special parallelogram, you get that diagonal. And that's U. So if you were to solve this for W2, then you would get W2 is equal to U minus W1. And that is called the vector component of U orthogonal to V. Now, what does the W2 look like in my other diagram? Because I have two diagrams here. No problem. It's similar. It's orthogonal to V, so there's this 90-degree angle here, and the sum of these two guys give you back the U. W1 plus W2 gives you U. Now, W2, I just gave you the formula for W2. It's easy. The formula for the actual projection, W1, is not going to be pretty, but I think you're ready now. Here it is. Theorem, the projection formula. And it does use the dot product, so you want to fill in the box here. So if U and V are non-zero vectors, the projection of U onto V is, first we'll do the notation, the projection of U onto V, that tiny subscript notation, is going to be a vector, and here's the thing, it's a scalar multiple of V. In other words, it's parallel to V. So in parentheses here is the scalar. So, but the scalar is not going to be pretty. You're not going to like it. It's a weird fraction. The numerator is going to contain the dot product of U and V. And the denominator, you can do one of two ways. I'll give you two choices. It can either be the magnitude of V squared, or let's see if you remember. Do you remember that the magnitude of a vector squared is the same as the dot product of the vector with itself?
Yeah.
Anybody remember that weird, strange property from last week?
Yeah.
Yep. Now I'm going to give you another version of this formula. This is the same as a scalar times the vector V. Okay, fine. Well, what scalar now? Well, it's going to give you the same scalar, but a different kind of alternate formula for it. So I want you to recall from last week that, do you remember that this theorem that the dot product of two vectors can be found in another weird way besides U1 V1 plus U2 V2, you know, taking the product of the components and adding them together. Because when we were finding the angle between two vectors, do you remember that formula? And this was a formula that's, I mentioned, is really important. It's going to be on the midterm, it's going to be on the final, all that. Since this numerator is U dot V, I could substitute that instead into finding projection like that. Yeah. And then if my denominator is still going to be the magnitude of v squared, I could do a little bit of reducing to lowest terms, which I'll do here. One of the factors of magnitude of v is going to cancel, if you will. So an alternate projection formula, if you know the angle between the vectors, and that's very rare. So full disclosure, I rarely use this version of projection. I rarely use it, if ever. My favorite is this one right here. This first one I'm giving you, okay? Now, there's another thing that is will be asked of you, a scalar component of u in the direction of v. Well, what is that? So the picture is if v, so here's v, here's u again. If v were a unit vector, what would be, and so your projection is a scalar times a vector. But if v were unitized, that is essentially the scalar component of u in the direction of v. So what is that? There's two versions of it. The two formulas are, you can choose whichever one you want. A magnitude of u cos theta is 1, or if you don't know the angle between them, nobody gave you that information, don't try using that version. The scalar component will be u dot v all over magnitude of v. That's what's known as the scalar component. So why is that? Well, how come it doesn't look like this? Well, the way it is if you took one of these magnitudes of v and moved it over here and put it underneath v, I'll do a little bit of scratch over here. So you still have the u dot v, and one of the magnitudes of v is down there, and you move the other magnitude underneath the vector v, this is now a unit vector pointing in the same direction as v, and this right here is the scalar component right there. That's why that's true. And then similarly for this other formula, which is not my personal favorite, if you moved the magnitude underneath the vector v there, then you get the unitized version of v, and then you simply take the scalar component there. So one or the other there. And yes, this stuff is going to be on a quiz and exam. Like, don't even go, oh, I don't care about this. It's not going to be on the exam. Now, I do want to say that okay, now let's look at some a basic example just with projections, and then we'll do an actual application of it. Okay? For those of you who are like, I don't get what you use it for. It's used for a lot of things. Okay, so here's a couple vectors, u and v. Fine. We're going to find the projected vector of u onto v. So basically, they're asking us to find proj, this is the notation, u onto v. That's what they want. Okay. If we use the formula that says, okay, the dot product in the numerator, it's going to be a scalar times a vector. And there's two choices for your denominator that I like, either the magnitude of v squared or the dot product of v with itself. Now I want to say something before I do this problem. And you may want to even make a note to yourself, because this is weird. It's backwards from what you would think. When you project a vector u onto the vector v, you're projecting u onto v. In the formula, who shows up the most times? Does the vector u show up more or the vector v? Even though the vector u is the one that you're projecting, who shows up the most times?
V.
V. Isn't that interesting, huh? Let that sink in. So when I ask you to project u onto v, v shows up 3 times in the formula. In fact, it's going to be a scalar multiple of v. If I had asked you for the projection of v onto u instead, then u would have been the one that showed up most times, because it would have been a scalar multiple of u. Please know that order matters, and it does make a difference of who's going on to who. Okay, here we go. So the W1 in my diagram up there, which is the same as the projection of u onto v, is going to be, we're going to be doing u dot v on the fly here. So 3 times 7 plus -5 times 1 plus 2 times -2 all over, and you're going to have the product well, we'll just have the magnitude squared, and then we'll multiply this with v. So what is the magnitude of v? Square root of 7 squared plus 1 squared plus 2 squared. And then you're just going to square that so the radical will disappear. So this is looking like, I don't know, what's 21 minus 5 minus 4.
Square root of 54?
Yeah, yeah. And so the numerator will be 12. There's your dot product. Square root of 54 squared is going to be just 54. And then this is the scalar times v, not the scalar component. Be careful. I'm going to reduce this to lowest terms because if you don't reduce, I take off a point every time you forget to reduce. And then we'll finish off this answer by multiplying the 2/9 with the vector v, and I'm always going to give component form as my answer just because that's how I roll, and distribute my scalar, and my projected vector is kind of weird, 14/9, comma 2/9, comma -4/9, and there it is. That's the projection of u onto v, or that would be the shadow that u makes on v if there were a bright sun shining down. Now we're going to find w2. The vector component of u that's orthogonal to v. So if you look at my diagrams up here, we found the w1 vector, that's the projection of u onto v, and now we want to find this other vector that's making a 90-degree angle with v, and if we add the projected vector with this vector w2, it would give us back our original vector u. And I call it W2. Your book and the homework don't, but I just name it that. Okay, so W2 is super easy to find. It's the vector U minus W1, and W1 we already got. So this is going to be the vector U, 3, -5, 2, minus this vector 14/9, 2/9, -4/9. And then you know when you're taking the difference of two vectors, you're going to get a vector. We'll simply take the difference of the x components and then the difference of the y components and then the difference of the z components. And then we do a little bit of arithmetic. And I usually use my calculator with the fraction command on it because don't give me decimals. I like fractions, -47/9. And then I think this is 22/9. Okay, so there's our W2. And then we're going to get the scalar component of the projection of u onto v. Be careful, it's not this scalar 12/54 or 2/9. The scalar component is the scalar that would be multiplied by the unitized version of v. And I already gave you two versions of the formula. You could use either one of these, whichever one in the right context. They didn't give us a theta at all to do business with. So don't go off in the weeds and go try to find a theta. You're never going to get there, okay? Well, you could, but you're going to be wasting time. You don't need to. Just use this. You already have the u dot v anyways. We got 12 as the dot product, and you already know that the magnitude of v, I think, was square root of 54. So the scalar of u onto v, and this is some of the notation you'll see. Instead of proj, you'll see scal, u onto v, is u dot v over magnitude of v. So that's going to be 12 all over the square root of 54. I'm going to clean this up just a little bit because I think that 54 is the product of 9 times 6, right? And square root of 9 is kind of a nice number, so let's simplify the radical. Ooh, now we can reduce to lowest terms. 12 divided by 3, ooh. Final answer, simplified form, and you don't need to rationalize denominators in my class. 4 over square root of 6 is the scalar component. And we're done with this problem. Yay, success. Questions?
Wait, why is the 6 in parentheses?
I was just multiplying 9 times 6 here. Was that okay? 9 times 6.
Oh, yeah, I see
9
it.
times 6 equals 54. Yay.
Yeah. I see what you mean.
Sorry, another question. On quizzes and exams, would we have to write the scale, like the part, and then instead of just writing u over v?
So this notation would be nice if you could take it on.
Okay.
I don't know if that answers your question. Hannah?
Yeah, got
Okay,
it.
just use it. I'm teaching you all kinds of new stuff in here. Yeah? So take it on like it matters. Now I'm going to give you a problem that's really, really key. And yes, you're going to see it on a future quiz or exam or both. Yeah, it's important. And it's kind of going to blow some of your socks off. So try to stay with me on this. This is an application of projections and why you even want to find the W1 and the W2. This is a common physics problem, like super common. Like they'll probably make you do this when the first couple of weeks of a physics class after they teach you vectors in 5 minutes. About 20 years ago when I was teaching this class, I had a student who like, wow, I wish I took this class before physics because now, you know, you're doing all these cool vector things that, you know, the physics prof just assumes we've seen already, and I'm lost. And I said, well, I'll talk to the physics prof. So I did. I asked this physics prof, hey, you know, why don't we make Calc 3 a prereq for Physics 1? Because, you know, a lot of students have complained to me they don't really get, you know, the full education of vectors in the Physics 1 class. It's just kind of boom, boom, boom. Okay, let's move on. You know your vectors. And this particular prof said, oh, sure, I go over vectors. I cover it in 5 minutes. That's all they need. And I went, okay, forget it. And so they never made Calculus 3 a prerequisite for Physics 1. But if I were the one advising students, I would always tell them, hey guys, physics is hard. Take Calc 3 before, because there's a lot of physics applications in there and you'll be thankful later. All right, so here's a picture of the physics problem, okay? So pretend there's a ramp here. This is a ramp, okay? Ramp. And let's say you had a boat and a trailer, a boat on a trailer sitting on the ramp. So I'm not very good at drawing because that's why I didn't get into graphic art, okay? Here's a trailer, say, with some wheels. I know that's pretty sad. You know, maybe a little hook here. Okay, and there's going to be a boat sitting on the trailer. I know, it's lame. Okay, here's a boat. Wow, that's really sad. Okay, you know, maybe it's a speedboat or something. I don't know. It's sitting on the trailer. Okay, together, the boat and the trailer weigh 600 pounds together. So the force due to gravity of both the boat and the trailer together, the force due to gravity is pointing down. So this force due to gravity, I'll just point it down. That's called F. And I hope you can appreciate that if I overlay a XY coordinate system on top of this picture, and you're always allowed to put the origin wherever you want, but it's always wise to put it in a place that makes sense. So X-axis, and then this would be overlaying the Y-axis. Do you see that F is pointing into the negative direction? So, and this point here, the tip of the vector, because it's a 600 magnitude, would be located at 0, -600, right there on the y-axis. So the component form for your vector F would be 0, -600, okay, for the weight, essentially, the force due to the weight of the boat and the trailer. Okay, fine. Now the ramp is a 30-degree angle here, fine. So what do they want us to get? Listen up, because this is coming. It's going to be on a test. What force is required to keep the boat from rolling down the ramp? So let's just say that if you were standing here and you were pushing against the boat and the trailer because you didn't want it to roll down the ramp and, you know, hurt something, what force would you be pointing or pushing with to avoid getting run over? Okay, that's question 1. Question 2 is, if the tires had feelings, what force must the tires withstand? Okay, so the picture for A and B look like this. You're basically going to resolve the weight vector, this vector F. You're going to resolve it into 2 vectors. You're going to resolve it into you're going to project the vector onto the ramp. So you're going to project, we're going to need to first project V onto the ramp. And that magnitude is going to be the force that's required that you're going to have to push. And then the picture of that, if I were to shine a bright sun here, and the sun, I know suns don't point upward, but the ramp is now the ground. So you have to sort of think upside down. The projection of F onto the ramp is going to be the shadow, and it's going to be this green vector here. That's our W1, essentially. That's going to be the projection of F onto the ramp. And then the force that the tires have to withstand, that's going to be our W2. Here's our W2. That's going to be the force that the tires have to withstand. So if the tires were make a 90-degree angle with the ramp, that would be the force there. So the magnitude of W2 is what they want for part B. So now you got the picture. Okay, big problem. They did not give us a vector on the ramp. They did not give us a vector on the ramp. So how are we going to even project this weight vector onto the ramp if they didn't give us one? So this is the hard part. You have to create a ramp vector out of thin air. Well, that's impossible. I can't just create something out of thin air. Sure you can, and you're gonna. In fact, we're gonna create a unit vector just to make it easier on ourselves, which means the magnitude is gonna be a 1. Okay, so the magnitude will be a 1. We're the boss, we can decide, it doesn't matter. We're just gonna do that. And then this ramp vector, I'm gonna just draw a picture of the ramp vector right here. Here's the ramp vector U. He's got a little magnitude of 1. And he's making an angle of 30 degrees with on flat. Well, that's not your x-axis, but remember, I could translate that F1 over here on my my XY coordinate system. And so now he's making an angle of 30 degrees with the positive x-axis. So if I were to transfer all of this messy diagram onto a nicer looking force diagram here, you'd have your F, your weight vector here. Down here is -600. You've got your little ramp vector here. He's making an angle of 30 degrees with the positive x-axis, and he's only 1 unit in length. And in fact, you can get his component form because I taught you how to get component form last week. And the magnitude of U is what again? Somebody help me out.
Sine at 30. Oh, wait, sorry.
What is the magnitude? Excuse me, sorry, I'm using incorrect notation. We're not.
It's
doing
1. Sorry. I was
It's
thinking
1.
about, yeah.
Because we said we wanted it to be a 1 to make it easy on ourselves. So it looks like 1 times cos 30 is just, hey, cosine 30, which I think is square root of 3/2. And then the other component is sine of 30, which I believe is a half. Cool, cool beans. Okay, so we're going to project F onto U. So that's going to give us this vector here. That's projection of F onto U. Okay, onto U. Get my little subscript in the wrong spot. Sorry. Now I'm erasing everything. Oh, we're turning into a big mess here. Okay, so the projection of our weight vector onto our cute little ramp vector is going to be the dot product of U and F. That'll be easy to get. It's going to be a scalar times U, essentially, divided by the magnitude of U squared. But this is just 1 squared, which is 1. So now we just have to worry about taking the dot product of these two vectors. So we're going to take the product of their x components plus the product of their y components divided by 1 and multiply that by U. Okay? And of course, 0 times anything is 0, and -600 times a half, I believe, is -300. So the projected vector is -300 times our unit vector. Now, I'm not even going to bother figuring out the rest of this vector because I just want the magnitude of this, because that's going to tell me how much force I need to push against the trailer and the boat without getting run over. So what is the magnitude of this scalar multiplied by the vector? And I taught you how to do this. Magnitude is always a positive number. So without even doing the whole square root of the sum of the squares of the components, I'm going to skip that. I'm going to do a quick and dirty way. it's going to be the absolute value of negative 300, oops, which we know is positive 300, times the magnitude of u. But I already know the magnitude of u. It's what? Somebody help me.
1.
Thank you. And then 300 times 1 is?
300.
Yep. And what are the units here? What are the units? Like I'm going to, when I'm pushing against this boat to prevent myself from getting run over, am I pushing with a force of 300 inches, 300 miles, 300 newtons, 300 pounds, 300 joules? What?
Pounds.
Pounds.
Pounds. Very good. And units matters. And we're done with part A. Part B. If the tires had feelings, what force would they be withstanding right now? Without them, I guess, blowing out or, I don't know, getting a flat. So we're being asked to find W2. So because W2 is equal to the vector we were doing business with and projecting, minus the W1, which we got up here, we have to get this vector, and then we are going to have to do the square root of the sum of the squares business here, okay? So the problem now is we are going to have to resolve this into component form. So let's do a little bit of scratch here. What is negative 300 times that unit vector that we found? And we'll just distribute this scalar of negative 300 over our cute little unit vector. So when we do that, and then we'll reduce to lowest terms. Oh dear, what are we going to get? That reduces to negative 150 square root of 3, negative 150. Okay, so there's our W1 in this formula here. So the W2 can be found by taking our weight vector, that's F, with components 0, negative 600, and we're going to subtract that from this vector with components negative 150 square root of 3. First component, second component is negative 150. And then you know how to subtract two vectors. We're going to take the first component of 0 minus a minus. Minus a minus is going to be a plus, obviously. And then the second component will be the difference of the y components. And again, we're going to have another minus minus. Got to be careful. A lot of minuses floating around here. Yikes. And then doing the arithmetic here, I'm going to get 150 square root of 3. And I think the y component is negative 450. Fine. Am I done? No, because they actually want the magnitude. So you're going to now whip out the calculator and take this yucky looking square root of the sum of the squares of the components. And I'm going to take positive 450 squared because that obviously gives me the same as negative. And I'm going to round to the nearest whole pound just because it's about 520 pounds. So the tires have to be, they're pushing down perpendicularly into the driveway or the ramp with 520 pounds of force. Okay, and that's another nice application for dot product. So now you know a couple of applications of dot product. One, you can use it to help you find the angle between two vectors. We went over that last Friday. And another one, you can use it to help you resolve a vector like this weight vector into the sum of two other vectors. One that's parallel to the vector you're projecting and the other one that's perpendicular to the vector that you're projecting. Very common physics application. Okay?
Yeah. What does that say up there? In the with the two dots for the year? Negative 300.
I don't know where you're pointing.
I think that says scratch.
Scratch. Yeah, when I do a little side in the margin, scratch work, sometimes I'll just say scratch. Is that okay? And I'm sorry if my handwriting is pretty lame.
Yeah, that's to say,
Scratch, just a little scratch work on the side for you. I needed to do this in order to do the rest of the problem, right?
Yeah.
Okay. Does that make sense?
Yes.
Okie dokie. Cool. All right. Let's do another application of dot product. There's more. Oh my goodness. You're going to be using the dot product from here all the way to May. It's not going away like ever. All these vector key concepts that we're doing in the first week or two, we're laying the foundation in order for us to do calculus 3. You can't do it without the vectors. They're super important. So let's talk about work. Now, work is another very common physics application. So what is work? I'm going to give you sort of the baby version, and then we're going to jack it up to be more of the on level with how we roll. Basically, work is the magnitude of your force times the distance that an object moves. And work is a scalar. It's not a vector. So basically, work is equal to the magnitude of a force times some distance that an object moves after being subject to said force. Okay, now you have to be careful here, because if somebody's pushing, with some force on an object, like, let's say I'm pushing against some really, let's say I'm pushing against the wall of my house, and the wall doesn't move a single, millimeter, because it's the wall. Believe it or not, no work has been done. What? But you did all this work pushing up against your wall. Yeah, I know. But that's not the work done on the wall. That would be a different kind of work. That would be work done by me, calories, expended or whatever. That wouldn't be the work done on the wall object. Okay, so what I'm trying to say in my own sweet way is that if the object doesn't move, then no work has been performed on the object. Kind of weird, huh? All right, so let's do a picture. Let's say this is a huge piece of granite, a huge rock. And let's say it's sitting on the ground. And let's say the front part of it is located at point P. And let's say somebody pulls on it with some rope or something with a force that's parallel to the ground. And let's say after pulling on it for a while, in the same direction there, parallel to the ground, let's say the object actually moves over here and ends up at point Q. Well, this right here is a distance. And so in this case, the work would be the magnitude of F times the distance moved, but that would be the magnitude of the vector PQ. Now, folks, usually you're never this lucky, so please don't ever use this force formula. Well, then how come you even gave it to us? Because like I said, I was giving you the baby version. Here's the thing. Do you notice that F and PQ are exactly parallel in order for this formula to be true? Usually you're not that lucky. Usually the force vector is a little off kilter and it's not exactly in alignment or pointing in the same direction as you're moving. So if the constant force is not directed along the line of motion, which is more common than not, your picture is going to look a little different. So we'll do the same piece of granite sitting on the ground. Here it is. Hasn't changed. Here's the ground. Okay. And let's say the rope, and so let's say you're pulling, but you're not pulling in exactly the same direction as your line of motion. It's making an angle of 30 degrees with the horizontal. So your work, and let's say the rock or the granite ends up over here again. So you're still going to have a distance here. That's not going to change. And your work is going to be the projection of F onto the ground, or the PQ vector. Take the magnitude of that times the distance that the object moves. So this is the key. And I don't usually use this formula because we're going to use some knowledge about trig to help us clean this formula up. So let's do a little bit of trig here. I hope this doesn't bore you. But if I drop a perpendicular down to here, I have a right triangle. Okay, and the projected vector is this vector right here. This vector I have in red, the adjacent side length is the projection of F onto PQ. So if you use a little bit of trig where cosine theta is equal to adjacent over hypotenuse, then you're basically saying that cosine theta is equal to the magnitude of your force vector onto the ground, the PQ vector, all over the hypotenuse, which is this length here, but that's just going to be the magnitude of F. And then I'm going to solve this little formula for the magnitude of the projection of F on a PQ. Well, how come? Because I'm going to replace this factor in my work formula with this answer. So it's going to turn out, after you clear fractions of this little formula by multiplying both sides of the equation by magnitude of F, and then you're going to substitute it there. So your work formula is now going to be W cos theta times magnitude of F times the distance the object moves, which is the magnitude of PQ. So that's one formula you're allowed to use. And it's a great formula to calculate work. But it's usually only good if they give you a theta. What if they don't? So I want you to recall something. Do you recall that the other day when I gave you the angle between U and V vectors, that cos theta was equal to U dot V all over magnitude of U, magnitude of V? Remember this? And then the alternate form is solving it for U dot V. I'm hoping you remember this version of the formula over here. So how does that help us? Well, I want you to look over here. Look at the right-hand side of this formula. Doesn't it have the same feel as this stuff over here, cos theta times the product of two magnitudes? Looks the same, doesn't it? It does. So we're going to use this theorem backwards, and I claim that these two formulas are equivalent. An alternate version of finding work is just to take the dot product of your force vector with the PQ vector, and you'll also get the same answer. Well, which one of those formulas should I use? Whichever the word problem is sort of alluding to in context. Like, look at what the pieces of information you're getting, and then use that to help you pick which formula is going to be the quickest. Okay, so I have two examples for you, A and B here, for example 5. I'll give you a hint. One of these word problems is going to involve the first formula, they're called the projection form. The other word problem will use the dot product form. Let's see if you can pick out which one is the most appropriate to use for which word problem, okay? And it's not hard. You're going to laugh, it's so easy, okay? Yes, there's no trick. So take a look at letter A. To close a sliding door, a person pulls on a rope at a constant force of 50 pounds at a constant angle of 60 degrees. Find the work done if the door moves 12 feet to its closed position. Be sure and give appropriate units in your answer. What do you guys think? Should I use the projection form or the dot product form for work?
Projection,
Good. How did you know, Kimberly?
because it gave you an angle.
Awesome. That's exactly right. Yeah, they gave you the distance. The 12 feet is the magnitude of PQ part, and they gave you the force magnitude. It's 50 pounds. So your work is going to be cos 60 degrees times the magnitude of F, 50 pounds, times the distance that the object moved, door moved 12 feet to close. Let's see, what is cosine 60? I think it's a half. And then 50 times 12 divided by 2. And then the units are what we call foot-pounds. And so the final answer, I get 300 foot-pounds, not pound-feet. And yes, it matters, and I'll dock you points if you do it backwards. Believe it or not, the work units are foot-pounds in the English system. I'm not making this up, people. I just report it. I've taken 2 years of physics. Although don't ask me too much of physics. It's been too long. I do know that F equals MA. And I do know how to calculate work. Okay, so letter B, obviously, by process of elimination, is going to most likely use the dot product form. So it's probably going to have a dot product of two vectors format, right? It's going to use this format. And let's see what they're asking here. Find the work done in moving an object from the point P to the point Q if the magnitude and direction of the force is given by this vector V. And the distance now is measured in meters, and the force is not measured in pounds, it's measured in newtons. This is the metric system. Give appropriate units in your answer. Huh. Well, first, we got to find PQ. You got to get a vector. Before you take a dot product, you can't take a dot product of a point with a vector, although I've seen some students do it, and then I just give you 0 points. I don't even give you partial credit in that case. You start going down a road that's like meaningless, yucky, I can't even give you partial credit for mercy points at that point. So PQ, you already know, I'm sure, because you did it on your quiz, how to find a vector given the initial point P and the terminal point Q. So you always do terminal minus initial because order matters for all these components. And then you do the arithmetic here. -4, 1, -4. Great. And so your work is simply going to be, we'll take PQ dotted with a V. So you're going to go, okay, what's -4, 1, -4, dot product with this V vector that they gave us the component form. And you're just going to do all the arithmetic here. And I get -24. Can work be negative? Oh yeah. Work can be positive, negative, or 0. And then what are the units? We don't have any foot-pounds going on here. And there's 2 answers that I will be okay with. One is Newton meters. Newton meters is units of work. And typically, if you take a physics course, you will see that Newton's meters is also known as J, joules. So joules are the unit of work in the metric system. Okay, and I'm done with this whole problem. Yay, we just did some work. Woohoo! Fantastic. Okay, so my question to you is, do you have any questions?
It's actually a pretty trivial question. When we're showing our work, do we have to show, because I could just look at P and Q and kind of figure it out and write it down. Do we have to show that subtraction in order to get full credit on our homework? Or
Yeah, I want to see an intermediate step, Kimberly. Okay, so here's the rule of thumb. Let's say you had a distant cousin taking this same class over at, say, Grossmont College. And let's just say, we'll be charitable here, they're a slow learner. And let's say they were trying to ask you for help on this problem and you go, oh, sure, no problem, let me show you my work. And then when they looked at your PQ vector, they're like, I don't know how'd you get that? And you're like, well, I did it in my head. And they're like, lost, deer in the headlights. You get what I'm saying?
Yeah, I do. Oh, thank you.
So if you just put at least, I'm not asking you, sometimes it is a little bit trivial, but every little thing. But this is kind of key. This is sort of key knowledge here of terminal minus initial. And so it would be helpful for your cousin if they at least saw that intermediate step of how you got the PQ. And that's what I want to see. I want to see how you got it. There's some other reasons too, Kimberly. I don't want to get too much in the weeds, but let's just say since I've been teaching remote, I have found that some students use some apps and websites and they type a problem in and they get the answers. And a lot of times the answer, they'll even show intermediate steps, although sometimes they skip them. And the student just copies it down and then they just, and then there's the answer. And they don't even really know how they got it. Does that make sense?
That's understandable. Yes.
Yeah, I mean, in my syllabus, it says the discretion of the instructor to do oral exams. And believe me, I have discretion and I will use it, maybe even this week. I don't do it all the time, but if I see some things that seem kind of fishy or I'm not buying, or I just want to test to see if you really can walk me through a problem or not. And I've had people pass my oral exams fine. But I want to see if you really know it. So I may give you a problem that's very similar, maybe just change the numbers. We'll have a little private Zoom chat and you'll tell me how you did it. And, I in the last year, I just want to say that I've had some successful Calculus 3 oral exams. And I've had some that aren't so successful where the person, they wouldn't admit to cheating, but they had no clue on, even though they got like a 97% on this one exam, how to walk me through any of the problems. And then they said, oh, well, I used, I don't know, they said some weird formula card. And I go, oh, great, let me see it. And they said they lost it. So moral of the story, For integrity's sake, show me intermediate steps. Okay, I'm done with this. Any other questions? Okay, congratulations. You are now done with section 13.3. That's projections and the dot product and all that good stuff. So now you're experts at projections. Well, you'll be an expert after you do some homework, right? And folks, I encourage you to come to me during office hour or 15 minutes before class, because I'm always here early, if you want to look at homework problems. I don't obviously have time during class to do homework problems, but I'm totally willing to get to class early, see you in office hours to do any of my math lab homework problem you want to look at. No problem. You know, I'm here. But if you don't ask, and I'm not a genius. I can't read minds. You have to come and get help. Further, I've had students who they don't do much of the homework and their quizzes are, you know, kind of lukewarm. And then they don't really study much and they go, I think I got everything. And they don't really go over my feedback. When I grade your handwritten work, let me just tell you, I'm going to upload it back to you in the submission comments. So when I post your grades, which most likely will be Wednesday, I need you to open up Canvas, look at your score, and then download your handwritten work again. It's going to have my handwriting on it. I'll tell you which problems, you know, where you lost points, and you want to make sure you correct your error or whatever it was. And then also go look in my math lab and see what the correct answer is. Because on your paper, I'm not going to write the correct answer. I just mark. I usually find where you first go off into the weeds and tell you, hey, this is where you started going off the deep end. You know, your first mistake. And then you go figure out the solution. Now, if you're still lost and you still don't get it, that's when you want to come ask for help. And I have students who never did the asking for the help because, well, I know stuff. And then they never question. And there's a famous old rabbi who said, shy students are not very good students. And I agree with him. Why do you think that's true? Why do you think shy students are not good students?
They never clarify things.
Yeah, they never ask when they get stuck. Oh, well, the teacher won't, you know, or my classmates may think I'm dumb or whatever. Who cares? Who cares? It's more important that you get your education. You're paying for it. Get it. Who cares what other people think? All right. You'll probably never see them again after this class is over. Okay. So now let's get into cross product. New topic. Cross product. What the heck? You know a dot product, but a cross product is different. So we're going to look at the cross product, and then we'll look at applications of the cross product, including physics applications, of course. So take a look at the definition, and the definition is going to be very unsatisfying, but I want you to be patient because I'm going to get you to the actual way you're going to do it. But the cross product, and notice they use a cross here, so it looks like a multiply symbol, but that's different from the dot product. You read it as U cross V, U cross V. Got my double quotes there. So what is U cross V? Well, this is just the definition. It's a scalar times a vector. Hey, we've seen that before, I know. So this scalar, and the vector is also, I'm going to call it n hat. It is a unit vector. Well, who's n hat and what? Just don't worry, I'll walk you through it. The scalar is going to be kind of weird. It is the sine of the angle between the two vectors multiplied by the product of their magnitudes. That's the weird scalar. And then that's multiplied by some funky unit vector. And the funky unit vector is a vector that's perpendicular to the plane containing u and v, according to something called the right-hand rule. Yeah. And the angle theta is the angle between u and v. So now let's look at a diagram, okay? And yes, you have to know the right-hand rule. Okay, so here's u and here's v, and you can think of this plane, this flat plane, as being the plane that the two original vectors here are located in. And if you curl your fingers, you start to curl your right hand. Can you guys see me up here? Stop looking at your notes. Look up here at my camera. you start curling your fingers through U, and then they curl through V. And then the direction that your thumb is pointing is exactly the direction that that N vector is pointing. And if you're left-handed, please don't get a resentment. You got to use your right hand, not your left. Okay. So you first start curling your fingers. Here's fingers. That looks pretty bad. And then they continue curling until you sort of make a half fist and your thumb is kind of sticking out there. And so N is pointing in the same direction as your thumb. Okay. So your N would be here. It's just a unit vector. Now notice the U cross V is taller than the N, and it might be. So that N is getting stretched by the scalar, and that scalar is sine theta times the magnitudes product, where theta is this angle between U and V down here. Now, folks, you're not going to use this definition to get your cross product, truth be known. I never do. Well, how do you get your cross product? I'm going to tell you. And this is the key right here on the next page. You're going to use what's called the determinant formula for the cross product U cross V. What's a determinant? If you've already taken linear algebra, you know this to be true. If not, the determinant is a pure number that is associated with square matrices. So what's a square matrice? It's a matrix that has the same number of rows as it has columns. Okay, here's a matrix right here. We're going to look at a matrix that's a 3 by 3. And when you take the determinant of a matrix, instead of the brackets to denote that you're trying to take its determinant, you have straight bars. Well, that looks like absolute value. It ain't. It means take the determinant. Now, this determinant is odd. And if you do not use the determinant method on your handwritten work, I don't care if your answer is correct, I'm going to take away points because I want you to use the determinant method. I use it. You have to use it. Well, you're being really anal retentive. Okay, fine. You know, how come it's always your way or the highway? Sometimes it is, sometimes it isn't. In this case, it is. And believe me, you'll thank me later when we do another problem in this same section, as well as when you take a Math 254 linear algebra class, which is basically fun and play with matrices, you will thank me then that I taught you how to find a determinant of a 3 by 3. I'm actually going to first teach you how to find a determinant of a 2 by 2. If you have a 2 by 2 matrix, A, B, C, D, the determinant, which we denote with the bars, can be found by taking the product of the elements along the major diagonal, whatever those values are, A times D, and subtracting the product of the values along the minor diagonal. And so this is going to be some number. Okay, that's a 2 by 2 determinant. Okay, we need that fact in order to finish out the 3 by 3 determinant. Well, what's a 3 by 3 determinant? Well, you're going to have a matrix that's 3 by 3. The top row is going to have the standard unit vectors, I hat, j hat, and k hat. The second row is going to contain the scalar components of U, and the third row is going to contain the scalar components of V. Okay, that's how you start. I want to see this on your paper. If I don't, you'll get points taken off. Then what? I'm going to show you how to expand along the first row. That's how we're going to find this determinant. There are alternate ways for finding determinants. You'll learn that in a linear algebra class. I don't have time to teach you that. So when we expand along row 1, what that means is you're going to copy I hat, j hat, and k hat down and leave a lot of room. Because your I hat is going to get multiplied with a 2 by 2 determinant, and then you're going to go minus a 2 by 2 determinant times j hat plus a 2 by 2 determinant times k hat. That's expanding along row 1. Now, be careful because this is a minus here. And then this right here is a plus. And you don't want to put those backwards. And a common student error is to think that it's always plus signs, but this has to be a minus. Well, how come? I would love to tell you, but then I'd have to start teaching you a Math 254 class. So I don't have time. Just to say you first would have to look at the matrix of cofactors and never mind. Okay, so what is this 2 by 2 determinant here? And what's this 2 by 2? And what's this 2 by 2? Watch closely is how I get them. I look at where I hat is located, and I temporarily block out the row and column that he lives in, just temporarily, and look at who's still standing. Those values get put in his corresponding 2 by 2 determinant. Okay? So then how do you get the 2 by 2 determinant that goes with the j hat? Well, again, you look at j hat where he's located, and you temporarily block out the row and column that he lives in and look at what's left. And then the values u1, u3, v1, v3 would be there. And then finally, the 2 by 2 determinant for k hat, block out the row and column that he lives in and get his corresponding 2 by 2 determinant. Okay, and then you're going to actually take the 2 by 2 determinant. So here you're going to get some scalar multiplied with I hat. So it'll be u2 v3 minus the product along the minor diagonal, the numbers u3 multiplied with v2. And then you're going to go minus a scalar times j hat. First multiply the major diagonal values, u1 v3, minus the minor diagonal values, u3 v1. Plus some scalar times k hat, major diagonal product minus the product of the elements along the minor diagonal. And there's your result. Now, folks, this is a vector. So the key point that I need you to get is when you take a cross product of two vectors, you get a vector. And this is completely different from dot product, because if you recall, when you take the dot product of two vectors, what do you get? Do you get a vector or a scalar?
Scalar.
Scalar.
Scalar. Big difference. Big difference. Okay, now let's do some cross product, shall we? U cross V. So the first thing I want to see is I want to see the 3 by 3 setup. I hat, j hat, k hat along the top row. 1, -2, 1 on the second row. 3, 1, -2 along the third row. So you're going to get a 2 by 2 I hat minus 2 by 2 j hat plus 2 by 2 k hat. 2 by 2 for the I hat are the elements that you obtain when you block out the row and column that I hat lives in. And similarly, the 2 by 2 that you get when you block out j hat's row and column, and then the 2 by 2 that you get when you block out k hat's row and column. So here you're going to get -2 times -2, which is 4, minus 1 times 1 I hat, minus, remember this is a minus here, please don't blow this. I see people getting, even on midterm 1, I'm going to put a cross product on there. You don't want to, leave points on the table by silly mistakes. A silly mistake being accidentally having this minus be a plus. And oh, I forgot. Nah, I'm not merciful there, because you get your access to your notes in Course Reader when you take quizzes and exams. So if you copied this down in your Course Reader correctly, I hope you won't blow it. Okay, take the major diagonal product minus, and the product along the minor diagonal, major diagonal minus, and be careful, there's a lot of minuses floating here. You're going to have 1 minus a -6. Uh-oh. 3 I hat minus a -5 j hat plus 7 k hat. I personally like component form, so I'm going to put this in component form because it looks better. That's just my opinion. Okay, there's your answer for letter A, a nice vector. Fine, but what if you did it in reverse order? Would you get the same answer? When you do the different order for dot product, you get the same answer. Okay, watch out. I hat, j hat, k hat. This time I'm going to put the components of V along the second row, and the bottom row has the U components. And yes, order matters for the setup. So if you do this whole 2 by 2 times I hat, 2 by 2 j hat, 2 by 2 k hat, I'm going kind of fast here. Final result, the vector with components -3, -5, -7. So what do you notice when you compare the results of A and B? Does order matter when you take a cross product?
Yes.
It does. And so what's the relationship? Well, one is just the opposite of the other. In fact, that's going to be one of the properties of cross product, which is nice. Now, what happens if you take a cross product of a vector with itself? That's possible, you know, hey, just to do the 3x3 setup here, 3x3 determinant. And it's going to turn out, what's going to happen is, and I'm going to sort of do this on the fly. You're going to get 1 times -2 minus 1 times -2. So that's going to be 0 I hat minus 3 times -2 minus 3 times -2. Oh, 0 j hat plus 3 times 1 minus 3 times 1. And normally you're not get, I want you to put the intermediate steps, but I'm kind of in a hurry. Oh my God, I don't get 0. I get the 0 vector. Will that always happen when you take the dot product of a vector with itself? Uh-huh. Yeah. And in fact, you'll always get that if you take a vector dot product with itself or a vector dot product, I mean cross product, sorry, I misspoke, cross product with a vector that's it's parallel to, okay? So quick weird question. Can you take the cross product of 2 vectors in the plane? What does plane mean? Not a jet plane, but I taught you that plane means what?
2D?
Yeah. Can you do a cross product of vectors in 2 dimensions? No, it's meaningless. Well, what am I trying to say? Anytime somebody asks you to do a cross product of 2 vectors, it's understood that you're in 3 dimensions. In fact, there's no other dimension that you can do a cross product. Like if somebody gave you some vectors in 4 or 5 dimensions, which we won't work with here, but if you take a linear algebra class, they work with 4-dimensional space, 5-dimensional space, 10-dimensional space. They're all over the place. You can't do a cross product unless you're in 3D. Okay, so it's very, very restrictive. Fine. Now, dot product you can do anywhere. Dot product, knock yourself out. That's valid in any space, any dimension. Cross product, not so much. Okay, let's do a couple theorems back to back. The first theorem, we're going to look at algebraic properties of the cross product. And the second theorem, we'll look at geometric properties. So let's just hit it, boom, 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 get this done here. I know I'm working overtime here. Yeah, it's 9:45. Do you think I don't know what time it is? I know what time it is. I'm trying to get through some of this so we don't have, on Wednesday, I will finish up cross product, but remember Friday is a holiday and Monday is a holiday, so I don't get to see you. So I gotta work as much as I can this week. Okay, U, V, and W, those are vectors in space. What does space mean? 3D. So then what? Well, U cross V will always be the opposite of V cross U. And we saw that in a previous example, because when we did the reverse order, we got the opposite in sign. Okay, so that's always true. Now, what if you're trying to take the cross product of U with the sum of 2 other vectors? No problem. You can either do it that way, where you do what's inside parentheses first, then take the cross product, or you can distribute. That's also valid. So cross product allows you to do some distribution over a sum. Nice. What if you have a scalar C? So C is a scalar. And they want you to multiply that with the cross product. Well, you have choices. You could just do the cross product first, like it says here, what's inside parentheses, and then multiply that result with the scalar. Or there's two other ways to do. You can first multiply the scalar with U, and then take the cross product of that with V. Or if you prefer, first take the scalar multiple of V with the scalar C, and then take the cross product. All 3 of those are equivalent. Pick your poison. Number 4, oh, I don't know what happened there. if you take the cross product of any vector with the 0 vector, this is the one time where order doesn't matter. You actually can do this in reverse order and get the same answer, because the answer is going to be the 0 vector. That's because I have a little vector on top of it. If you don't just put the number 0, the number 0 without the little vector notation on top is a scalar, and you want to make sure you make the distinction between scalars and vectors. Okay, if you take the cross product of a vector with itself, we already did this on the previous page, and I hope you remember, we just get the 0 vector. Fine, and then this, I'm going to put a star by number 6 because it's interesting. If you take the dot product, this is interesting, it's got a mix and match of dot and cross product in the same statement, with the cross product of V and W. You can either do it like that, if you like, or you're allowed to first take the cross product of U and V and the dot product of that with W. Wow, that doesn't look like it would match. It will. And this is called the triple scalar product, aka also known as the box product. And you heard it here first, people. The book doesn't tell you this good stuff. I'm giving you some good vocabulary. If you take vector calculus next fall, say at UCSD or at San Diego State, you'll know stuff. Okay, let's do some geometric properties. Number 1, U cross V is orthogonal. That means essentially perpendicular to both U and V. And a lot of students, when I write this down, they go, yeah, whatever, who cares? And then I give them a true false question that actually involves this concept, hint, hint, and they get it wrong because they never really soaked in this fact. They never really got this. And it's unfortunate that you don't, if you don't get this, then you really aren't getting the idea of cross products. Let's go back to the original picture here. That's kind of a mess with the right-hand rule. Let's just look at what this thing is saying. Oops. Let's look at what this thing is saying. Anytime I use the erase on my Microsoft Surface Pro, all hell breaks loose. Okay. So here's a picture. If you get this picture, you'll be good. Look at U and V down here. And then the cross product is that kind of pink, purpley, fuchsia vector. Do you notice that that vector here is making a 90-degree angle with both of the originals? Please say yes.
Yes.
Yeah. And that is exactly right, because the cross product is orthogonal to the two guys that help create him. And so the way I like to think of it is this is mom and this is dad. The baby, the offspring, the cross product is orthogonal to both mom and dad simultaneously. Cool beans. That's all. It's a very basic fact, geometrically speaking, but it's key. It's key that you get that. Like if you don't get that, we're in trouble. Like then you miss the whole point of orthogonality of the cross product. Okay, now number 2 is interesting. It says that the magnitude of that cross product will be exactly the same as sine of theta, the angle between the two original vectors, multiplied by the product of their magnitudes. That's interesting. Okay. Okay, fine. And then number 3 says, and this is cool, I would keep this one under your hat. U cross V is equal to the 0 vector if and only if. Do you guys know that IFF stands for if and only if?
Yes.
It's a very special statement. It means it's what we call in math a double header. In fact, sometimes you'll see an if and only if instead of the words if and only if. They'll put a double-headed arrow. That means you can read the sentence forwards and backwards and it's still true. That's different from an if-then statement. An if-then, you could only read it in a forwards direction and it's true. If and only if is awesome because you can read it in both directions and it's still maintains its validity. If and only if u and v are scalar multiples of each other. Now, from last week's material, what does it mean when two vectors are scalar multiples of each other? Does anybody remember the relationship geometrically?
Isn't it if you multiply, for example, u times some number, you're going to get v
Yeah.
by one number?
Yeah, it would be u is equal to cv or v is equal to cu. Correct, Hannah? And further, Hannah, can you tell me what that means? What's the relationship between those two vectors?
I'm not sure.
Okay, anybody else want to jump in there? I'll give you a hint. It starts with the letter P. The two vectors are...
But they are parallel.
They're parallel to each other. Very good. So here's a really cool thing. If you're in 3D, this weird thing only works in 3D. If you are too lazy to show me that the two vectors are scalar multiples of each other, because that's kind of a pain in the rear end, and you want to quickly show me that the two vectors are parallel, just show me that their cross product gives the zero vector. Now, why is that true? Because look, if you have u here and v is parallel, so they're either pointing in the same direction or they're pointing in the opposite direction, either way. If you try to use your right hand here, so here's my fingers wrapping around, you aren't going to get anywhere because your thumb or your fingers can't really, let's say you do your fingers through here. Your thumb, you think, oh, it's going to be pointing in the up direction. It's going to be a dot. Your thumb is going to be a dot, essentially. It's not going to be pointing anywhere. Okay. And so why is that? Well, because your sine of your angle between them, sine of 0 degrees or sine of 180 is going to be 0. So you're going to have 0 magnitude, so you get the 0 vector. So you can read this in any direction. So I'm going to read, I'm going to read it in the opposite direction. If u and v are parallel, that means their cross product is the 0 vector. Okay. Number 4, and number 4, I'm going to put a star by because this is key. Yes, so you're going to have this on exams. If you take the magnitude of u and v cross product, you will get a very cool number. Really? Like, what's the number? It is going to give you the area of a parallelogram having u and v as adjacent sides of the parallelogram. I'm going to prove this, and then I'm going to kick you out of here, okay? So I'm going to prove number 4, and then we'll finish for today. So moral story, we're going to revisit some more cross product stuff Wednesday and hopefully get to some applications. We didn't get there today. So besides the right-hand rule, I mean, you didn't really get anywhere here. Sorry. Okay, so how about number 4? Let's draw a picture. Here's u, here's v. If you can imagine, those are two adjacent sides of a parallelogram. I'll even draw, by dotted lines, I'll draw the other two sides of the parallelogram. Fine. If you had to find the area of this parallelogram, I hope you remember that area of a parallelogram is the base times the height. Really? Yeah. So the base is this length here. That's the base of your parallelogram. So I already know that my base is going to be the magnitude of u. Fine. Times the height. Well, what's the height? It's not the magnitude of v, okay? Here's the height of the parallelogram. You may have seen this in a geometry class. If you drop a perpendicular from the tip of v down to the base, this right here is your height. So what the heck is that? Let's do a little bit of scratch over here to try to get the height. So if I knew the angle theta between u and v, and I use a little bit of trig, that sine of theta is equal to opposite over hypotenuse. The opposite side length of this little right triangle I'm doing business with would be the height, which is unknown, and I wish I knew what that was. And then the hypotenuse is the magnitude of v. Now let's solve this for height. Solve this little formula for height. by multiplying both sides of the equation by magnitude of V. And you'll get height is equal to sine theta magnitude of V. And now you can substitute that into your area formula. So area is equal to, you know, magnitude of U times magnitude of V times sine theta. But then by property number 2, which I didn't prove, but we're going to use it now. Which one is that? Well, if you look at property 2 up here, it claims that the right-hand side, which is sine theta magnitude of U magnitude of V, it gives you the exact same result as the magnitude of the cross product. We're done by property 2. So QED, and there I'm done with the proof. Okay, so there you have it. I'm done with today's lecture. I'm going to stop the recording. If you have any quick questions, I have a few minutes I can stay after class and answer.